Hello everyone, so let's start today's session and we'll take up the previous GATE and IES questions and solve that, so it will give the more clarity for us. So let's start. The first question: the plastic analysis, which of the following pair these are correctly matched? So geometry of steel section, shape factor, rectangle is 1.5, so that is, we know that that's 1.5 it is. So this is correct. Round it is 1.7, square it is 1.7, so the answer is C. At the location of plastic hinge, so what it is, at the location of plastic hinge, radius of curvature is infinite, moment is infinite, flexure stress is infinite, so radius of curvature R is not infinite. Okay, it's not, but radius of curvature is infinite. Okay, so the answer is C. So moment is, you cannot have an infinite moment, but also you cannot have an infinite flexure stress. Next, move on. A rectangular steel section of width B and depth h has been stressed to a yield point sigma y up to a depth of h by 4 from the bottom and top. Okay, face under the action of a moment m. The magnitude of the moment is, okay, so this is, it takes a little while. So what they are saying is that, like, I have a rectangular section. Okay, so like it's going quite good. Okay, so this is a rectangular section. Okay, so now this has been stressed to yield point sigma y, means, so this is your, I take this as my equilibrium axis, and the stress distribution is going to be this way. Okay, so up to this particular point, v by 4. Okay, and this is actually linear comes, and this is okay. Okay, so this is a straight point. So how much this is? This is actually h by 4. Okay, h by 4, and this is also h by 4. H by 4. This is h. Okay, and this is b, and the remaining thing up to here. So this is h by 2. H by 4 plus h by 4 is h by 2. The remaining is h by 2. So what is the moment capacity? So how we calculate the moment capacity? Now this part is under C, and this part is under a plastic stress, that is yield stress sigma y, and this part is under elastic stress. Okay, so we can do this in a many way. The first thing is that, like, let's take this force as C1, this force as T1. Okay, and here this force as C2, and this force as T2. Now C1 and T1, this is, let's call this as a Z1. Okay, Z1, and let's call this is as Z2. So moment, what I can take is that it is C1 into Z1, okay, plus C2 into Z2. So what is C1? C1 is equals to, should be equals to T1. This should be equals to, what is this? It is sigma y. Okay, the area is B into h by 4. So what is Z1? Now look at this. This is Z1, uniformly stressed area. Okay, this h by 4 and this h by 4, and this is the center. From here it is going to h by 4 by 2, h by 8, minus this also is going to be at h by 4 by 2. So Z1 is going to be h minus h by 4. Okay, So how much you're going to get? We're going to get 3h by 4. And then what is C2? C2 is equals to, it is average stress, sigma y by 2, and area, it is B into h by 4. Okay, cool. And what is Z2? Now Z2 is equals to, look at this, this is triangular portion. So this is from here to here, it is 2/3 of h, sorry, h by 4. This is also triangular, 2/3 of h by 4. This is 2/3 of h by 4 plus 2/3 of h by 4. Okay, so moving on, what I'm going to get here, so it is actually 2 so it is 4h times of 3 by 3 into 4. So 4 get cancelled. I'm going to get h by 3. So substituting everything here into the formula. Okay, so m is equals to, what is C1? C1 is equals to sigma y into b h by 4. What is Z1? 3h by 4, right? Plus it is sigma y by 2 into b h by 4, okay, into h by 3. So what you are going to get common? Sigma y b h square. Okay, so here this is going to be 3 by 16, 3 by 16, yeah. And also I can take, what is this, 3 by 4, actually 1 by 4 is common, yeah. If I take 1 by 4, I'm going to get 3 by 4, yeah, plus this is going to be 1 by 6. Okay, so the answer is going to be sigma y bh square by 4 into 6 4s are 24, 6 3s are 18, it is 4. Okay, so it is 22 divided by 24. So it is going to be 22 divided by 24. So this is going to be 11s, 12s. So therefore it is, the answer is 11 by 48. So sigma y into bh square divided by 48. Therefore the answer is C. You have to solve by yourself. You need to understand each step here. I hope it's clear. So now here, for an I wave, shape factor is 1.12. Okay, fine. Shape factor is 1.12. The factor of safety in bending is 1.5. If the allowable stress is increased by 20%, okay, for wind and earthquake loads, then what is the load factor is? So what is the load factor formula? So load factor formula is equals to, okay, Fy into Zp by F allowable by Ze. Okay, so here what is given? Fy is there, right? Zp is there. 20% has been increased. Okay, allowable stress and Ze. Okay, so if I do it here, so load factor is equals to, it is 1 over 1.2 Phi by Fa Zp by Ze. So this is how much? 1.2 into factor of safety 1.5 Zp by Z2, it is 1.12. Okay, the answer would be, answer what we will get is that it is going to be 1.4. The answer is D. Okay, just check by yourself. Okay, going on to the next question. The ductile structure is defined as one for which the plastic deformation before fracture is actually much smaller than the elastic deformation. No. Vanishes? No. Is equal to the elastic? No. The answer is D. Okay, think about it. Think about the questions and think about the answers. You will understand. Next, assertion. The shape factor of a circular section is less than that of an rectangular section. No, the shape S for circular section is 1.7 and S for rectangular section is 1.5. The assertion itself is wrong. Okay, compared to the rectangular section, a circular section has more area near the neutral axis than the extreme fiber. Yes, that's true. If you look into the rectangular section, okay, right. So if you draw the neutral axis and if you draw the circular section, pardon my drawing. So what it is. So more area is closer to the neutral axis than the less area. Here it is actually evenly distributed. So reason is correct, but assertion is wrong. Okay, and even that actually explains why it is so. Reason is correct. So A is false, but R is true. Okay. So moving on, shape factor for the section shown in the figures. Okay, it also takes a lot of time here. Okay, so first of all, since it is symmetrical, this is going to be my neutral axis. Okay, so to calculate what? To calculate the I, okay, I leave it to you, okay, to do it. First you need to calculate I, okay. So I you would get, and y maximum, you know, y maximum is equals to 100. Okay, and I also I can write quickly here. So I is equals to what? So I is equals to uh, it is B 40 into, okay, 100 cube by B cube by 3 base less it is 100 it is 160, 100 minus 40 160 into 20 cube by 3. This is I, this is y maximum. The z you will get it as 275,200. Okay, then zp is the main thing. So zp is equals to what? Area by 2 into yc bar, sorry, yc bar plus yt bar. Okay, so what is the total area? So total area is simply half of the area. So, right, so 40 into 100, 160 into 20. So area by 2, it is 40 into 100, okay, plus 160 multiplied by 20. And what is yc bar? Oh, now yc bar and yt bar will be same, okay, some area, because in symmetrical they are going to both here. So this is what you need to calculate. So yc bar will be, how are you going to calculate? So it is 160 multiplied by 20 multiplied by 10 plus, what is this answer? This is 40 into 100 multiplied by 50 and divided by the same thing, 40 into, sorry, 160 into 20, okay, plus 40 into 100. So y bar plus section, you are going to get something, okay. I don't have the calc, just do the calcs here. But zp, what you are going to get is equals to, it is 46400, okay, 464, sorry, I'm 00. So the shape factor S you are going to be equals to 145 by 86. Okay, the answer is B. Okay, we'll continue in the next video. Thank you.